phase, not in solid state. Okay, so you have calcinide, the green color, and analyte, pink color. So they are in liquid phase. They stored in these two reservoirs. So they can, we have two pumps on the bottom. They can drive this two different solution through the electrical surface to do electrochemical reaction, charging and discharging. So sort of we have, actively in liquid phase to do, battery chemistry. So that's a major difference from the solid state battery. The principle, the battery principle is still applied, but just the state of the active materials. And because of this, design, then flow battery has a lot of advantage over solid state batteries, including lithium-ion batteries and lead acid battery and nickel metal hydride batteries for large-scale energy storage. So let's finish I think that's good enough for this animation. Let's go ahead to do more, to highlight a little more technical merits about redox flow batteries. So because of this architecture, so you can say when we after charging, okay, so we will have this charged to liquid, they're separated and they stored in two different tanks. So that means physically they were not able to contact to each other. So that means they are safer in terms of energy storage, okay? And also you can say we store the energy material in the tanks, and however in a chemical reaction, they were performed on the electrical surface. And the electrical surface can be also independently changed on decrease side or increase side. So we call that energy and the power decoupling. So that's an advantage feature for flow battery. So you can tune how much power you need, and you can also tune how much energy you need by changing the size of tank and change the size of the electrical surface. So that cannot be done by the enclosed solid batteries. Okay, so that's another major feature: the safety and the separation of energy and power. And also in the liquid phase, and we have much better collectors for electrochemical reactions, so they can run much higher current compared to lithium-ion batteries. For example, lithium-ion battery can run up to 5 milliampere per square centimeter. That's it. You cannot go much higher. But for flow batteries, and depends on the electrolyte nature, you can go you can run the battery up to 1,000 milliampere per square centimeter, like a traditional hydrogen oxygen fuel cell. So that's a high power system. Okay. Then, so how can we integrate the flow batteries into the existing electric grid? So showing here, it's another cartoon. So right now I'm showing the traditional, the basic component for electricity grid network. So you have power plant produce electricity, and we have grid network and deliver electricity from power plant to different users, including household and commercial buildings. So that's a basic scheme and the layout of a traditional electricity network. Okay. Then people start to think about, we start to integrate renewable energy into the electricity network. Okay. So that's a direct connection to supply, solar and wind energy into the grid network. But it works, but it's not perfect. Why? Because I said the renewable energy, they are intermittent and available. They are not stable. So that means we have to have an energy storage medium in the renewable energy and the electricity network to solve the problem. So that's how the flow batteries, chemical energy storage, fit into this new generation of the electricity network. Okay. And also, we can integrate the flow battery technology into end users. So we can have localized integration of renewable energy. So we can put, windmill, small side windmill and solar panel and the top of the buildings, and coupled with the small size flow batteries. So we can have localized energy generation. So we can minimize the energy from power plant. We can minimize the electricity transportation from a greater electricity network. Okay. So also we can use the stored electricity to charge our cars. Okay, we can direct charge to current lithium-ion battery cars. Also, we can, if we have high energy flow batteries, we can direct pump our electrolyte solution into flow battery support cars. So overall, so another point that we want to emphasize, we can also use stored electricity to do electric catalysis, convert electricity to chemical fuels into hydrogen and carbon hydrate, okay, like alcohol and methanol, methanol and ethanol. So overall, so I'm showing here, it's a smart grid picture. So we will have, by integrated energy storage technology, so we can have reduce the burning of fossil fuels. We will have a more environment benign energy system and more energy efficient. So that's an ideal picture we are looking forward to. So then after you have this basic idea, I would like to give a brief summary about the historical development of the redox flow batteries. So the concept of the using low redox active material in fuel cell was back to 1955. You can see the scheme here. So people, that's a very infant idea back to that time. So people start to use two different redox couple, iron and tin redox couple for the air, for the oxygen electrode and the fuel electrode. So that's how people start to use redox active materials in fuel cell design. So that's a sort of beginning of the story. Then when time reached to 1970s and 80s, so LASAR, so the big research organization in US, LASAR, so they start to develop real design of low batteries. So for the energy supply for spaceships, okay, that's their major purpose, right? So they have looked at the LASA, the scientists at LASA, they look at the bunch of redox active material, including iron, inorganic material, iron, chromium, bromine, and palladium. So they look at the number of the redox active material for as the anode and the cathode materials. So eventually they end up with a combination of iron and chromium chemistry. So they developed iron, chromium, acidic redox flow batteries. So showing here, that's a very old picture to show the stack design for the original iron chromium redox flow batteries. So at that moment, they developed some up to 1 megawatt hour size stack flow batteries, but they start to fade out because there are some several technical weakness about this design. Then in the same time, so a patent was filed on the zinc halide batteries. It was not for flow batteries, just sort of a liquid batteries. But then with time going, people adopted the chemistry of zinc halide in flow batteries. So you can use halide as chloride, bromine, and iodine. So the popular one, so people use for flow battery is the zinc bromide. Okay, the zinc bromide. That's a bipolar sort. So we will talk about this little more later. So this technique was mainly developed by Exxon and Good. These two companies for zinc bromide flow battery. So later in 1986, so the Australian chemist Skylas from I think it's from South Wales. Let's see, yeah, I guess it's South Wales University in Australia. So she started to more seriously test the vanadium chemistry, and she invented the all vanadium redox flow batteries. Okay, and then with time going, and there's some more inorganic chemistry based flow batteries developed up to 2009. And from all different battery chemistry and vanadium chemistry and zinc bromide flow battery, they have been really commissioned by a number of companies. So showing here on the right, that's a UET large stack of lithium flow batteries. So this company was spun out from Pinel with by my colleagues. So starting back to 2012. So they have been doing pretty good in this area for using lithium chemistry for energy storage. So showing here on the left to the UET picture. So that's the flow battery from a red flow. That's a zinc bromine redox flow batteries. So after 2009, there's a big shift about the development of the redox flow batteries. So we, chemists started transition from inorganic chemistry to organic chemistry. So right now, there's a big research effort on developing organic material-based flow batteries. That's a real research I'm going to show you guys today and even later. So why we are interested with the organic redox flow batteries? So that's because there are some limitations, technical problems with the conventionalized vanadium flow battery and zinc bromide flow batteries. So let's look at some technical details about vanadium flow batteries. So the chemistry is quite simple. On the anode, you have vanadium 3 plus ion reduced to vanadium 2 plus at minus 0.25 volt. That's the negative side. And on the cathode side, you have vanadium 5. Okay, vanadium 4. Sorry. Okay, is vanadium 4 is oxidized by 1 electron and plus water to form vanadium 5, okay, at 1 volt. So overall, you have more than 1.2 volt cell voltage. So the good thing about vanadium flow batteries, because it use sulfuric acid electrolyte, it's very conductive. It can run high power performance. So it can run up to 500 milliamp per square meter current density. It's very highly power, very high current performance. Also, the chemistry is very simple, very robust. So vanadium battery can be, so people have tested for several thousand cycles. So pretty robust, the chemistry. So what are the major problems with this technology? So the major thing is the cost of the technology. So this technology is quite expensive because the vanadium oxide is quite expensive. So overall, based on the vanadium oxide price and also the cost of other materials, so the overall energy cost for this type of technology is up to $450 per kilowatt. Okay, that's quite expensive. So U.S. DOE, the Department of Energy, they have a goal to reach to less than $150 per kilowatt hour for large scale energy storage. So apparently the vanadium oxide won't be able to make that goal. So also the battery use acidic electrolyte. It's corrosive. It's hard. It takes effort to maintain. And in terms of chemistry, even though you are using fan membrane for this chemistry, so you still have the electrolyte crossover. You have the vanadium, either one. So it depends on the nature of the membrane. You will have vanadium 3 or vanadium 4 or 5 cross to the other side. So those are some major problems. So let's look at zinc bromide chemistry. So the chemistry is also very straightforward. So on the anode, you undergo zinc reduction, 2-neutron reduction to zinc metal. And on the anode side, you have bromide undergoes oxidation to form bromine. Okay, the voltage is very high. You can reach almost 1.8 volt for this design. The good thing about this zinc bromine battery, it's a simple chemistry, no materials, and high voltage system. So what's wrong with that? So this battery can only run no current. Why? Because zinc, when you deposit zinc from zinc metal electrode, so it will form zinc dendrite. That's sharp structure. So this sharp structure, it is not good. It will poke the membrane. It's not good. So that you have to run no current to avoid the formation of this type of sharp structure on the zinc metal surface. That's a problem. Also, you have the bromine. That's very corrosive, and that's not environment healthy. And also it has electrolyte crossover because bromine is a neutral molecule. No matter anion exchange membrane or cation exchange membrane you are using for the batteries, the bromine will cross over. Okay, that's a problem. So that's a drive force from the limitations of vanadium batteries and the zinc flow batteries. We want to start the new chemistry based on redox active organic compound. So organic compound, typically they are made from carbon, hydrogen, oxygen, or nitrogen elements. So no, resource problem. Okay, they can be low cost in large scale production. And also the performance, so you can use synthetic chemistry, simple synthetic chemistry to tune the performance of these organic materials, okay? And also you can couple to other simple inorganic materials to make hybrid low batteries. So basically, so you have two ways to do, to design redox flow battery using organic materials. You can run organic materials reaction in non-aqueous solution. So traditionally, all these chemistry, they perform in aqueous solution, right? So they have hydrogen water splitting problem. They have hydrogen evolution, oxygen evolution. So in non-aqueous, so you can solve this problem to reach high voltage system, okay? And on the other side, you can also, to do the flow battery chemistry in aqueous solution like traditional vanadium and bromide. And we can still have safety system and high energy, high power system. Okay. So moving on, I'm going to highlight a couple of technology we have been doing at USU. So showing here the first technology we developed early last year. So that's a combination of two molecules. So cell reaction, you can say. So we have aromatic bipyridine system, that's MV. So that's MV molecule. So that's an anode material. So it has a redox potential. You can see from CV at minus 0.45 volt. And for the cathode, we use a very classic, tempo molecule. It has an oxidation potential at 0.8 volt. So overall, you can see it has a 1.25 volt voltage, which is comparable to the vanadium flow batteries I talked about. So showing here it's a redox chemistry. And the good things about this design is they are cheap. Okay, so for the active materials, the MV, so the conventional price for mass of biology, the MV is only about $1 per kilogram. And the tempo chemical is also very common chemical. It's only about $6 per kilogram. So those prices are significantly lower than the vanadium oxide, which is more than $15 US per kilogram. Okay, so another thing is, so these both compound, they have very fast collected for redox reactions. So shown here, there are some battery performance data. So they either figure A here, so we can say the battery can run high current from 40 up to 100 milliampere per centimeter meter, the charge and discharge curves, okay, corresponding to different current density. And shown in the figure B, so we have energy efficiency and voltage efficiency and economic efficiency. So the blue trace on the top, you can see here, follow my curves. So the economic efficiency is very good, just stay about around 100%, okay? Now, energy efficiency and voltage, they decrease with the current density. That's typical for any batteries because you have fixed internal resistance. When you increase current, you increase voltage loss. Okay. Then at the 60, we have 60 milliampere per centigram. We have power density energy efficiency up more than 60%. That's some energy efficiency number we want to achieve at least. So showing figures here, that's a cycling performance. So you can see for the 100 cycle, it's fairly stable. We see slightly decay. Okay, we still see decay. It's not it's not perfect design. So I will tell you why. Okay. So basically, so this battery, so we are running this battery in neutral sodium chloride solution, not acidic or alkaline solution. That's a benign electrolyte system. So we are also, we do not use expensive membrane. We use a low-cost anion exchange membrane. So using chloride as charge transfer carrier. So we have good performance as I talk about. Okay, so why we have capacity decay here? Okay, so the capacity decay is due to this neutral molecule. Okay, it's not an ionic compound. It will not compare with the anion because anion will only stop the cation species like MV here. It's a dication species. But for the tempo, it's a neutral compound. So it's, when you run it back, it can go through the membrane to reach to the MV side. So still we have crossover problem. On the other side, the capacity, the total energy density, we can only reach 4 watt-hour per liter, which is much lower than vanadium battery, vanadium flow battery, and the zinc batteries. Okay. Then, so that's a problem with these tempo molecules. That's a problem we have been trying to solve. Okay. So the target, but we are trying to replace tempo with shown here. I'm not sure you are chemists. So that's a very classic, very commercially available molecule. So we call the ferrocene. It's like a sandwich, iron atom sandwich between two fine membrane. That's like sandwich. We call the sandwich ferrocene compound. That's a very common compound. So in order to make sure the ferrocene compound can be soluble, so we have tested a number of the conventional available molecules shown here. So the best thing, they are not really good because their solubility is not good enough. They all have solubility less than 0.1 molar. Okay, that's not good. Then eventually we identify a new molecule still with a major component of the ferrocene and attach it with this ammonium pendant arm. So at PM, when I was at PM, one of my colleagues report this chemistry for non-liquid batteries. Okay, and when this molecule have TFSI anion, it shows pretty good solubility in carbonate, in organic solvent, but not soluble in water. So we did some study, found this type of molecule, when you change the anion from TFSI to chloride, so it will be water soluble. Okay, so that's the background information. And then my students, Bohr and Cam, so they undertook this new task. So they, developed a new way to synthesize this ammonium pendant functionalized ferrocene with chloride anion. Okay, and they can make this compound very easily and large scale. Okay, high yield, very high yield and large scale. And they did the test. Okay, they find this molecule. Okay, the chloride ferrocene ammonium compound is extremely highly soluble in water, more than 4 molar in water. Okay, that means we can reach to more than 100 amp-hour per liter capacity from this compound. Then we combined this compound with methyl-biology, so we can reach to 1.05 volt. Okay, then even the voltage is lower than our first generation, but however, both compounds, they are very water soluble, so they have higher capacity. So when you have capacity combined with cell voltage, still this battery can have very high energy density. So showing here some basic study about the kinetic information about this molecule. We don't have to worry about too much. The bottom line is, so this molecule is very electrochemically active and the kinetics is very good. So showing here some battery performance. So our batteries, when we combine this new compound, this ferrocene compound with methyl-biology, so we can have the energy density shown here, more than 50 watt per liter. So that's the highest energy density known for aqueous organic batteries. Also, it's liter. Okay? So we already beat, in terms of energy density, we already beat the vanadium batteries. So shown here is energy, kind of performance. Same thing. This system can run from 40 to up to 100 milliampere per square meter. And it also has similar energy efficiency as first one. So we can, at 60, we still have more than 60% energy efficiency. So the major technical merit of this battery is the stability. So we solved the early problem with our first generation. So the combination of the ferrocene compound with MV. So you can see for 700 cycles. So the curve here, the red, blue, red triangle and the blue rectangular. That's a capacity retention. You see this technology is fairly stable up to 700. We see minimum decay. Okay, the early one we only showed 100 cycles. This one we have 700 cycles. That's the best performance, second performance for organic fluid batteries right now. So recently we just get this published in the Journal of the American Chemical Society. So here's the reference. You guys can look at the details for this battery from this paper. So we have very good power performance for this battery. So we can at 0.7 molar, okay, we can have power performance more than up to 120 milliwatt per centigrade meter. That's almost close to the lower end of the traditional hydrogen fuel cells. Okay, it's pretty good. So that's some summary about the performance of this technology. So if we compare the second generation of organic fluid battery with reported organic fluid battery systems, so our battery is put by very high right now. So we can run 700 cycles with very good capacity retention at 99.99% per cycle, okay? And we have highest energy density, 52.4 watt-hour per liter. That's highest number for organic system. So most recently, my students, they also did some further improvement about this battery system. So they changed the membrane for this design. So they can say on the right side, they can, by using a new membrane, DSV membrane, they can increase the energy density, at 60 milliampere per centigram. They can, increase the energy density up to 75%. Okay, from 6% energy efficiency increase to 75% at same current, okay? Even at 40 milliampere per centigram, we have energy efficiency more than 80%. It's almost compared to acidic system used for the vanadium batteries. So overall, I think my time is almost there. I think probably 7 minutes more. So I give you a quick summary. So we are working on a new generation of fluid battery technologies using, low cost and robust Redox active organic materials. So we have some technology, as I showed, they are very promising for further development, and they have some, technical advantage over traditional vanadium batteries and zinc bromine batteries. Okay. So here, that's my group members, and so we have all boys in my group. They work hard, and they're smart. And so I also want to take this time to acknowledge the funding, the support from DOE and University Utah State, and also USTAR program to support our battery research. So sorry, I think I took several minutes more than what I need. So I would like to take any question you guys have. Thank you very much.
Well, that's fine. Thank you, Leo. That's a fantastic, very informative presentation. I've unmuted everybody. We have about 10, maybe 15 minutes for questions.
What about 8?
So please go ahead.
Yes.
Do we have a question coming in? Go ahead.
Thank you very much.
Sure, I guess I'll go ahead. This is Steve Clark. Question regarding what you think the potential costs could be. You commented that one of the vanadium Redox flow batteries was upwards of $450 per kilowatt hour. How low do you think this could potentially go?
You mean for vanadium system or for the organic system?
I'm not sure which one you mentioned, but one of them was upwards of 400.
Oh yes, yeah. So the vanadium. So I think you are trying to talk about asking the cost of the for the application. So for the vanadium battery, it has right now the lowest cost is still more than $200 per kilowatt hour. Okay.
Okay.
For the organic system, for the organic system we are talking about here. So in terms of materials, they are way cheaper than vanadium oxide. So overall, we did some cost estimation. So right now, the second system, the iron and the MV system, we can have the cost right now, just very basic cost estimation based on materials. Okay, we can the cap cost around 160 US dollars per kilowatt hour.
Yeah. Oh, that's very good.
Yeah, it's very close to the DOE target right now.
Yep. Okay.
Thank you, Steve. Appreciate the question. There was another one that we started with earlier. I think I may have cut you off. My apologies. Go ahead and throw any others out here or comments, whatever you have.
So this is Talis Blaylock. I have a question in terms of what kind of size and weight do you have for this type of solution?
You mean in my research lab, or generally speaking for the flow batteries?
For if you were to put together a production battery for this, what kind of size and weight and temperature considerations and things?
So the individual cell, okay, individual cell, that's we call the stack. That's a steel stack. The smaller stack is about 1 feet by 1 feet size. You can imagine that. And for this, within this 1 feet by 1 feet size, we can stack up to 20 individual cells together to form a stack. That's a small individual stack. And then you can use this individual stack to do modular, and you can cover them at 100, 200, as much as you want in series way or parallel way.
So in that 1 cubic foot stack, what's the capacity of that?
Capacity we can reach to 1 kilowatt hour.
So 1 kilowatt hour per cubic foot, essentially.
Yeah.
And how much does that weigh?
Oh, that's a hard question. I have never. You can. It's hard because you need to consider the stack is fine. I think we need to consider the weight for the solution, because I think for the I'm not sure what to concern with the weight, but I want to add more information about that. So the weight is not concerned for flow battery for the large scale energy storage, okay? Because it just occupies the same space, okay? You just need more space. That's something I want to emphasize. I'm not sure what the concern about the weight.
The reason I was wondering about the weight is what's the cost of the foundation or footing that you're building to put the battery on? Oh,
so I think how to say that? I believe, so my own understanding, the weight is not really concerned because you just not like you are using for car, okay? Because if you add the different weight for car transportation, that's fine. But you think you have stationary and storage, you just leave there, it's staying there. Nobody concerned with the weight, so it's more concerned about the volume. So I hope I answered. I hope what I told you makes sense to you. Okay.
Unmuted. I unmuted everybody's, and so somebody might need to mute who's doing some typing here. I don't mind you working while we're doing this. That's what we're trying to accomplish. But just check your mute. Okay, go ahead. Keep going with the discussion.
Yes. Yeah, I got a question. It's Oliver Gross here. Can you talk a little bit about it when you connect cells in the series? What things you need to take into consideration? And do you expect there to be any kind of degradation in performance, either in per cell voltage or in total capacity when you do that?
Yeah, I think as I said, so for the new technologies, and so the one we showed you, the second kit, so far the best performing organic system. So we did a lot of fundamental study and spectroscopy study after more than 1,000 cycle. So we haven't seen degradation, but we do identify what's wrong with our company. We still see minimal degradation, right? It's still some capacity. So it's nothing. It feels nothing to do with the chemical stability. We have some, system problem. So we need to do some engineering improvement. For example, so we found out there are some, the osmotic pressure problem. So these two sorts, okay, two different organisms, they have different, solubility. They have different interaction with water. So with time going, the water will migrate from anode side to the cathode side. That will affect the overall cell conductivity, and then so that's why we have needed capacity feeding there. So with time going, it flat out. So we will have some capacity drop, and we will say we are trying to build a larger battery, and to do even longer tests. See what other potential problems. So far that's one problem we have identified. So, but it's solvable. Okay, that we can find engineering solution to attack this problem.
This is Prabhakar. I got a question with regard to maintenance that may be needed. If you can imagine this as an energy storage installation that may run for several years, is there any periodic maintenance that's required either in the pumping system or the membranes or any other part of the system?
Yeah, I think you raised a very excellent question. I think for flow batteries, honestly, I think you have to concern with the whole system, not your active material. You have to also concern with the membrane. So that's something we, in general speaking, okay. So from the data of the vanadium chemistry, seems okay. The lithium membrane is fairly robust in the vanadium chemistry. So I have seen people run 5,000 cycles test battery testing with vanadium system. Seems very robust. Okay, and for our system, we have been we are in the process evaluating different membranes. So we are trying to identify whether we have membrane problems for the field. So that's something we are working on that. So so you have to make sure your active materials are chemical robust, stable. Okay? And the second, you have to make sure another possibility is the stability of the membrane. Okay, if your membranes are degraded, you will start to build up the internal resistance. That's another problem. You are right. And about the pumping, I think you have good pumping. It's easy to replace cement because it's outside. It's easy to replace it, to maintain. I think a major concern, you're right. If you have membrane problem, that's the maintain can be very challenging.
Thank you.
I think we have time for maybe one more question if we want to throw one more in there.
This is Kent Warner from John Deere. I'm curious, do you have any comments about the temperature requirements or capabilities over temperature range of this sort of battery versus some other chemistries?
Oh, we have some preliminary data about temperature performance. So ideally, depends on the application you want to use. If you are using field applications, more general field applications in the outside environment, you want to have your battery can run from I would say from at least minus 10 Celsius degree up to 50 Celsius degree. So that can be affected. This temperature range can be affected by the environment, summer or winter, right? So for our battery system, we have tested in this range, and we have observed, quite similar performance. Even at a higher temperature, we say increase the power performance because at higher temperature, the system more conductive. Yeah, so that's a good question. Yeah.
So is there an upper limit that you would expect then? You're saying it becomes more efficient. I'm assuming you also must get a limit there.
Yeah, you are right. Depends on the nature of the electrolyte. So for example, because the system we are using here, those are aqueous system. So that means you cannot heat up to 100 Celsius degree, right? You start to lose water. So I think, safely speaking, I think 50 Celsius degree is a high limit. I would say is an upper limit for the temperature control, and lower limit, I think you can hopefully you can goes down to -20. Okay, -10 is a good number too, I would say. So the reason you can even aqueous you can goes down to -10 Celsius degree, because when you add active materials, and also if you add some glycol mixed solvent, so you start to change the physical properties of the water. So the whole electrolyte they will have wider range of the melting point and boiling point.
Excellent conversation. Dr. Liu, thank you very much. Again, an insightful presentation. We're going to cut it off here. Just remember that this presentation will be available on our website before long. We'll make sure that everybody has access to that in case you want to refer to it again. Please feel free to contact Dr. Liu. Leo, appreciate your time. I might just put a plug in here. February 17th is our next, sorry, let me just, I didn't realize that I was still not on camera. It's just dark. That's why I had muted it. So anyway, February 15th is our next brown bag presentation, noon Mountain Standard Time. The title for that is Capacitive Wireless Power Transfer Systems for EV Charging. The presenter on that is Dr. Karama Freedy at University of Colorado Boulder. So we appreciate all your time, again, your interest, and we'll see if some good things come out of this. Have a wonderful day. Anything else in parting that we need to cover before we go? All right. Thanks again. We'll see you soon.
Thank you.
Thank you. Yes. Bye.
Goodbye, all.
Thanks. Bye now.